Lesson 4.4, found on page 135 of your big book, is basically a continuation of lesson 4.3. It's titled Problem Solving, Use Tables to Compare Ratios. So basically we're just going to build tables to compare ratios and make equivalent fractions. All right. A paint store uses rose pink paint by mixing 3 parts red paint to 8 parts white. A clerk mixes 4 parts red to 7 parts white paint. Did the clerk mix the paint correctly to make rose pink paint? Use tables of equivalent ratios to support your answer. So use the graphic organizer to help you solve the problem. All right, so we're going to get started by reading the problem. All right, so what do I need to find? I need to find whether the ratio used by the clerk is equivalent. Equivalent. Notice the beginning of this looks very much like equal. Right? It has the same root. So we're trying to find out if the ratios of the actual rose pink paint, 3 to 8, is equal to 4 to 7, if they're equivalent. All right, find what information do I need to use? I need to use the rose pink paint ratio, remember, was 3 to 8. And the ratio used by the clerk, which was 4 to 7. How will I use the information? I will make tables, is how I'm going to do it, of equivalent ratios to compare the ratios 3 to 8 and 4 to 7. So here we go. They gave us the tables already, so that makes our lives a little easier. Let's see if I can do this. Perfect. All right. So for the rose pink paint, I have 3 to 8. This would be times 2 times 3 times 4. 3 times 2 is 6. 8 times 2 is 4. 3 times 3 is 9. 8 times 3 is 24. 3 times 4 is 12. 8 times 4 is 32. So over here, I also have the times 2, times 3, times 4 to help us remember. All right, so 4 times 2 is 8. 7 times 2 is 14. 4 times 3 is 12. 7 times 3 is 21. 4 times 4 is 16. 7 times 4 is 28. All right, so now we're going to look for a pattern to determine whether the ratios in the first table are equivalent to the ratios in the second table. So we want to know if there are any ratios in here that are equivalent. All right, so the number 12 shows up twice. So we've got the number 12 shows up twice, right here and right here in the numerator. But 12 to 32 is not equivalent, is not equal to 12 to 21. They're not the same. Do you see any other that you can compare? 24. Nope, none of the denominators compare. That's the only numerator that you find in both, but their denominators are different. So no, these are not equivalent. So the clerk did not mix that paint correctly because the ratios have the same numerator, but they have different denominators. So we did it wrong. All right, on the back side, we're going to try another problem. In Amy's art class, the ratio of brushes to students is 6 to 4. So every student Every 4 students, 1, 2, I have to draw stuff to know what's going on. 3, 4 students get 1, 2, 3, 4, 5, 6 art brushes to paint with. All right. In Tracy's art class, the ratio of brushes to students is 9 to 6. Okay, so that's 1, 2, 3, 4, 5, 6. Okay, so I've got 6 students. They get 9 brushes. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 brushes for these 6 students in her class. Okay, so is the ratio of brushes to students in Amy's class equivalent to the ratio of brushes to students in Tracy's class? Use tables of equivalent ratios to support your answers. So we're going to eventually build some tables, but first we're going to determine what do we need to find. So we want to know whether the ratio of brushes to students is equal or equivalent. I should say equivalent. Let's change that. Equivalent in the 2 classes. That's what we're trying to decide, is if they're equivalent. All right, what information do I need to use? I need to use the ratio. So I need to use the ratio of brushes to students in each class. So that's the information I'll use. And how will I use this information? I will make tables. Tables of equivalent ratios to compare 6 to 4, and what was the other one? 9 to 6. All right, so that's how I'll use this information. All right, here we go. We're going to build a couple of tables now. So, first table, let's draw, and we'll make brushes and students. Okay, and the first one we already know is 6 to 4. Let's take it out 3 more spaces. Let's say 1, 2, 3. Build our little table here. There. And now we need to do that all over again. Brushes, students. Okay, and we know the first one, which was what, 9 to 6. 1, 2. Let's take it out 1 more. There. All right. So we'll find out whether or not it's equivalent. Okay, now remember this would be times 2, times 3, times 4, times 2, because this first one is times 1. Always. Times 3, times 4. There we go. All right, 6 times 2 is 12. 4 times 2 is 8. 3 times 6 is 18. 3 times 4 is 12. 4 times 6 is 24. 4 times 4 is 16. All right, so I filled out my first table. Let's take care of the second one. 2 times 9 is 18. 2 times 6 is 12. 3 times 9 is 27. 3 times 6 is 18. Let's see, 4 times 9 would be what? 36 and 24. All right, so now we're going to go along and look for matching numerators. Okay, we've got 2 18s, but that's the only one. All right, I'm going to highlight that so I pay attention to the 18s now. Now I have to look at the denominator, because even though I have matching numerators, if the denominators are not the same, then, oh, and look at that. They are the same. So we have equivalent ratios going on then. So if there are any matching numerators and denominators in the two tables that are being compared, then we do have equivalent ratios. So 18 to 12 is equivalent to 18 to 12, which means the ratios in the two, sorry, I ran out of room, tables are equivalent. So if you can find an equivalent ratio in two different tables, that means the two tables have equivalent ratios going on. All right, so now they're asking us, so the ratio of brushes to students in Amy's class is equivalent to the ratio of brushes to students in Tracy's class. Okay, so explain how you used a pattern to determine whether the ratios in the two tables were equivalent. Well, I saw that both tables include the ratio 18 to 12, since it appears in both tables, they must be equivalent. Period. All right. Tell how writing the ratio in the simplest form can help you justify your answer. All right, so neither one of these ratios are in simplest form, meaning there is a common factor between 6 and 4 that we can reduce 6 and 4 down. So let's do a little margin work for a second here. So 6 and 4 are both even. Therefore, they can be simplified by a form of 1, which is 2 over 2. 6 divided by 2 is 3. 4 divided by 2 is 2. So, let's do another margin work here. We've got 9. Oops, I'm not on the camera here. Can be divided by. This has these two numbers have a common factor as well, 3. So if I simplify by 3 over 3, 9 divided by 3 is 3. 6 divided by 3 is 2. What do you know? So when you simplify the ratios, whoops, that's really messy. When you simplify the ratios, you find that they are equivalent. Okay, just by simplifying them, I found out that they are equivalent. All right, let's take a look at our notes. All right, use tables to compare ratios. So your notes are draw a table for each set of ratios. So if you're comparing two sets of ratios, draw tables, start finding common numerators and common denominators, and guess what? These are not equivalent, because even though I have a 20 here, the denominators are different. And even though I have a 9 over here, the numerators are different. So these are not equivalent ratios. 4 to 3 and 5 to 9 are not equivalent. However, 3 to 8 and 12 to 32 are equivalent. Because once you start filling out the 3 to 8 table, you discover that there's a 12 to 32 in there already. So this actually is the most simplified form of this ratio. In other words, I could have taken this 12 to 32, divided them both by, what, 4? Yeah, divided by 4, and I would have gotten 3 to 8. I would have found that they were equivalent if I'd taken them down to their most simplified form.